Great, thank you, Ed. And to the last point about technical research, this is very much a research-focused presentation. We're moving away from the building envelope to mechanical systems. Yeah, really looking at some cool research we did last fall. It's named Cold Air Distribution, Novel Approach to Meeting Passivhaus Cooling Loads, and you'll see shortly why that is. Yes, this does not work. Okay. So, some background. Essentially, we have what we maybe can label a conventional approach to high-performance passive house buildings that we're looking to electrify, right? Essentially, what we have is three systems: a ventilation system, providing indoor air quality. We have a heat pump that's going to be doing space heating and cooling. And if we're going the full electrification, we're going to have a separate heat pump for domestic hot water. So three separate systems, right? And we're basically taking, what's available commercially that hasn't really been designed, except for the ventilation system, hasn't really been designed for passive house loads. We know they're nice and low, right? So there was a promise in passive house. If you invest in the envelope, you can simplify mechanical systems and save money. Well, in practice, we haven't actually realized that. We're still relying on the systems that are out there that are available to us. So we haven't seen those savings. So, and the challenge here, and some of you folks who have done the training will recognize the formula. This is the only math you'll see in the presentation. But this famous 10 watts per square meter of a heating load, right? And we know there's been examples of passive houses that have met all of their heating through just heating the ventilation air, right? The air we need for indoor air quality, we heat that up and we can actually meet all of our heating load. Right? The challenge is we can't really do that on the cooling side, right? If we do a comparison to the calculation, we get a much lower capacity for our air to deliver the cooling that we need, right? And this is essentially because we can't cool the air down to a temperature as much as we can raise the temperature up for heating. Right? So we're limited in our capacity. So this project is essentially, at least part of the project, and the key research piece is to see, well, can we actually boost the cooling capacity of our ventilation air by decreasing the temperature? And this work is actually focused on multifamily, which has higher ventilation rates than single-family home. If you look at like a per square foot or per square meter, we actually have higher flow rates. So those two factors combined, you can see we're edging up to that 10 watts per square meter for cooling. So this is our proposed system that we're looking at doing as part of this research project, is essentially taking our ventilation system and then heating and cooling that air. And that is going to be the only mechanism by which we deliver heating and cooling into the building. And if we switch to a hydronic system, so air to water heat pump, we can actually technically have one heat pump do all of the heating, cooling, and hot water. And so the goal here is we try to simplify the system and maybe save some costs. Okay, so the challenge. So this approach is actually called cold air distribution. It's actually something that's been done in industry, in industrial, and even some commercial buildings. Has not been applied to residential buildings, and we'll see shortly why. So we are targeting a delivery temperature of 5 degrees C. If you open up your refrigerator, that's about the temperature you're going to get from your refrigerator. Right? So if we do this, put this into a building, this introduces three key risks. Well, the first one might be obvious: occupant comfort. Right? So a key research question is, can we do this? Can we deliver this into residential spaces, such as bedrooms, living rooms, without causing occupant discomfort, right? Because you could expect really cold air is going to dump, it's going to create cold drafts, right? Second issue is condensation. You take a pop out of the refrigerator, especially in the summer, and how long does it take before it gets drops of condensation, right? Well, that could easily happen here. And then the third risk is mold growth. You think, okay, we're pushing air out of a diffuser. The area around the diffuser, so the drywall, could get quite cold and end up as a medium for mold growth. So last fall, this is what we set out to validate in a laboratory. So we actually used some space at the University of Toronto. They have a rooftop basically building that has 2 test chambers. So we set up basically small little mock bedrooms and tested out a variety of different parameters to see if we could make this work. Right, so some of the things we measured, we looked at, so we had some diffusers, just okay, what are the conditions of the air coming out of the diffuser, temperature, relative humidity, flow rate, and so on. Surface temperature, right, using IR camera. And we also had a thermal comfort station we used from the University of Toronto. It's basically a station that allows you to assess occupant comfort. So we placed that in the center of the room to see how it performed. And then we had a high-tech way of measuring temperature stratification, which was basically strands of toilet paper from floor to ceiling. In terms of what we did, so I mentioned 5 degrees C. We looked at different flow rates from basically a really small rate of 24 cubic meters per hour up to about 120. We looked at different air speeds coming out of the diffuser. We looked at different diffuser positions. Some of those who were familiar with the passive, you've been through the passive training, you might recognize the Coanda effect. So we were testing this out in cooling mode with the super chill there. And we also had another reference of ceiling mounted diffuser. And then a variety of different diffuser types. We scanned the market, we found some proprietary materials. We looked at a diffuser purely made out of insulation. And then a colleague got me onto some anti-condensation paint, which will show some interesting results. And then as a reference, some conventional diffusers, which we would all recognize. Okay, so I could spend hours talking about the lab work. It was very intense. I've just got a couple snippets of some of the challenges. I went in a bit naive. This is my usual work. So a lot of challenges that came up that were unexpected. So one of the key challenges initially, there's a big air handling unit in the lab that we made use of, and we were getting an 8-degree temperature difference. Literally from the air handling, it's about 2 or 3 meters of duct to the room, and we got 8 degrees temperature rise in that short distance. So I was like, okay, well, let's insulate around the ducts. And I got a nice shield wall of a mineral there and trying to get it all around. And that had almost no effect. And you're like, how is adding insulation not having an effect? Well, that was basically because there's too much surface area, right? So I and a colleague there at U of T basically painstakingly cut pieces of insulation to make a duct within a duct, basically equivalent of about 5-inch duct within the duct. And when I did that, in the end, I got to actually, towards the end of the experiments, I got down to less than 2 degrees coming out of the diffuser. So actually colder than what we were targeting. Another issue is thermal bridging. So I have this nice metal duct. I've double insulated it. It's like fiberglass duct insulation. It's vapor sealed. I've got it taped. But look, I got condensation. So obviously there was a weakness in that insulation somehow. You do your best, but there's a lot going on in the lab. And you get condensation. So a little bit on the results here of the project. So what we noticed really, in the thermographic images were great for identifying this, was where you have air leakage, you're going to have basically cold air coming out, and you're going to have condensation, right? So you can nicely see where all the leaks are here. So our solution is seal, and seal some more. And so after some work sealing up, you can see we actually get some really nice temperatures there. Right. So that was this was a very useful tool to identify where those leaks were. In terms of the diffusers, we tried a whole bunch. I can't remember the number now. I'm not going to spend time going through all these diffusers. Most of them failed. The key takeaways: if you have a diffuser made of insulation, that's going to work. So that's informing our next phase for the project. There were some materials that showed a bit of promise. We might try them in small quantities, but probably not en masse. And then the anti-condensation paint is a very interesting one here. So here's a diffuser. This is actually one of them that has made with a proprietary material. I don't actually know what it is. don't get much information from the manufacturer. But basically, the middle section is basically plain diffuser you get from the manufacturer. And I tested out this anti-condensation paint with different layers. So, because they said, oh, you need a certain thickness. I wasn't sure how much I was applying. And I guess, I didn't have one of the depth meters for coats. Anyways, on the left, there's 1 coat of paint. And on the right, there's 3 coats. And on the left, you can see there's no actual beads of condensation, but it was moist to the touch, right? So I touch it and I get a bit of moisture on my finger. On the right, with the 3 coats, completely dry to the touch. So this magic anti-condensation paint is actually working, which is fantastic. You wouldn't expect a product like that makes some wild claim to actually work, but it actually did. Other things that were causing condensation, basically any item that's in the airflow that's also exposed to the room air will get condensation. So you can see I've got sensor wire there going up, that gets condensation, it's dripping down. Tape, thin layer of tape, that's enough to cause condensation, right? It was a magnet for condensation. Here's a diffuser. This is a fabric-based diffuser, which actually didn't condense, but I've got a zoomed-in image there. The metal framing that was exposed actually did condense. Right? Now, like if this were properly constructed, we wouldn't have that exposed, but the manufacturer quickly produced a custom diffuser for me that I could test. So that was obviously missed. So pretty much any object, except if you have insulation. So to make some of my experiments work, that you can see I've got a diffuser here with lots of holes, and my phone is going on the wall. Sorry about that. Okay. Yeah, so I was plugging these, I was trying to cover them up so I'd be able to control the airflow and airspeed and stuff. And I started to tape them, and that wasn't working at all. So I just plugged them with little pieces of insulation, and that worked for avoiding condensation. In terms of surface temperature, basically, if you have a diffuser that pushes air out radially or in parallel to the surface of the diffuser, you're going to get cold temperature, which is, kind of obvious, but it's, we have this, testing to show this now, right? Whether it's ceiling mounted or wall mounted, if it's parallel, it's going to condense. If you have the diffuser pushing air perpendicular to the surface it's installed in, then we have no issues, right? You can see here 3 different diffusers. Even that one of those ones you might recognize on the right, and millions of these installed in Canada, those floor diffusers. That was not installed in the floor, it's installed in the wall, but it worked beautifully as well. And then if we look not just around the diffuser, but for these wall-mounted diffusers, what's the surface, like the ceiling temperature? How's that doing, right? And basically we saw any diffuser that is essentially projecting air horizontally, it's actually not a problem. You can see the temperature there. It's not, you can't really go by the colors because the scale changes, but you can see that the ceiling temperature, you can see the air pattern, but it's 24 degrees. That's 5-degree air coming out of the diffuser, and look how quickly it actually mixes and doesn't cause issues. Here's a, again, Home Depot type diffuser you can get, readily pick up. You can see this is a better color contrast just to see the pattern, but again, don't go by the color because the scale is different. You can see 22 degrees on the ceiling there as well. So even your conventional diffuser can actually work in this, work from a surface temperature perspective. Okay. Here's a fog test I did. I have a little video, but didn't want to chance it not working. But you can see, it's coming out thick, right, out of the diffuser, and it really quickly mixes with the room air, and that's why we don't get the cold surface temperature. Occupant comfort. We looked at this. This is. I tried to summarize, basically, there's an ISO standard that gives you classifications, A, B, C. I don't know if there's anything worse than that. And so, I was assessing this for all the diffusers. So I've got some 3 examples here from the diffusers we tested. We got the ceiling mounted, we've got one of these linear slot diffusers, which is wall mounted, and then I've got this conventional metal diffuser that is ceiling or wall mounted as well. And basically the ceiling mounted, I didn't get good consistent results, so that was causing occupant issues. You can see area of so these are 3 different positions. I moved the comfort station around the room, so there are different positions in the room. So you can see it was failing in certain areas. The other 2 there's a couple areas where it's category B, but that was like kind of just slipped below A, so I don't really consider that an issue. Temperature stratification from bottom to top, despite the really cold temperature, about 2 degrees C, which we'd expect in a passive house. So the temperature stratification was great as well. And then supply air speed. Generally, this didn't have an impact on the comfort. The exception is when I had a really high speed, bordering on about 5 meters per second. What was happening was such a small room, it was hitting the back wall and then coming down and causing an issue, right? So really, you just gotta watch the airspeed depending on the size of the room. Okay, a little summary here. So the 3 things we looked at: occupant comfort, we see, okay, we can mitigate that issue. Mold growth, with the right diffuser strategy, we can mitigate that. And then condensation, we do have strategies for diffusers now that we believe we can implement to mitigate or eliminate the risk of condensation. Okay, so just some recommendations. I don't know how much time I have, but probably not much. Okay. Yeah, I mean, just basically, you know, we're going to be exploring more of this, as I'll describe in a bit. But basically, you know, we need a sufficient amount of insulation, about 2 inches around the ducts. And we want to, there's a variety. I probably don't have time to really go through this. But the variety of recommendations we can take forward to actually implementing in some buildings. Which brings me to implementation. So we've actually received funding to implement this strategy in 6 different projects across Canada, coast to coast, from Victoria to Pictou, Nova Scotia, different sizes from 3 units to 42 units, market, affordable housing, different climate zones as well. So really exciting, huge diversity. So we can see, you know, prove out that this could be a universal solution across Canada. We're also going to have extensive post-occupancy evaluation, 2 years of technical monitoring, assessing the performance, as well as occupant engagement and assessment to get the feedback from the occupants of, you know, how do they experience this project or this solution. And thankfully, all the mechanical engineers on these build projects are on board to implement the solution. That's not always the case for innovative solutions. And that wraps me up with, I think, enough time, which is great. So do want to acknowledge CMHC. This, the previous research in the fall was actually funded under the Housing Supply Challenge Building for the Future round. So that was grateful for them to make this happen. And then just wanted to shout out to some folks that really helped on the project. Sheng Bo Zhang from the University of Toronto, PhD student there, was very instrumental in helping me. Wolfgang Hasper from the Passive House Institute in Germany, and then Kara Sloat, who couldn't make it tonight, a fellow engineer at the Hammerschlag in Joffre. So, and actually, a quick shout out to Greg and TMU for, thank you for allowing me to use the flow finder. That was helpful as well. So that is it. So thank you very much for your attention.